It's now my turn to be in front of you as a lecturer, not just introducing people or discussing a few other things. We're going to spend the next 1.5 hours together. The idea is that I present to you a few concepts or ideas about trustworthy AI and machine learning. And we have also actually created a hands-on kind of tutorial on Google Colab. And the idea is actually we can spend maybe half an hour there. So half an hour out of the 1.5 hours. Let's see how this will work, right? OK, so it's my pleasure to be here. The idea is that we're going to discuss about trustworthy AI in power systems. This is actually a work that we have been doing over the past couple of years. There's a number of people that have been working on different parts of this, and without them, this wouldn't have been possible. So first of all, many thanks to all of them, and some of them are also here today. And many thanks also to our funding. So this is part of the European Research Council grant, a study grant, that has allowed us to perform this research. OK, this is the outline. So you can see that I have a number of points. And if you also go to the slides, you can see that actually it's quite many slides. I'm not going to go through all of them. But first, I'm going to start getting a step back. So thinking a little bit or reflecting a bit about what is power systems, what are the challenges, and why AI can possibly create value and how, right? Then I'm actually going to skip closing the loop. I think it's a nice, framework. But I'm going directly to the neural network verification and the provable worst case guarantees. I expect that this crowd or you actually would expect something more concrete. So how we actually model things, give you some insights, how we actually perform the verification. You're going to see that it's nothing else than an optimization. OK, it's an optimization problem we're solving. We just use a few ideas there that we're going to discuss. Then I'm going to discuss about physics-informed neural networks. And we have also been doing some work on quantum computing. I do think there is, let's say, potential there. Carlton, I think, present a very nice overview. And many thanks also to Carlton for presenting one piece of our work there. I'm not going to discuss this. It's just for you to take a look at if you are interested in some more insights. So that this actually will leave us time to talk about or to spend some time on the tutorial on physics-informed neural networks. We thought that between the different parts that we have here, the physics-informed might be a more straightforward piece of code that you can start with, OK, compared to the other. So let's see how this will work. OK, so let's take now a step back. I don't know. I guess all of you do some work on energy systems or electricity. Have you ever taken a step back to understand what exactly this is all about? If you go online or if you've been at different maybe talks, people talk about power systems as the largest machine humans ever built. OK, we're talking about a very large network of interconnected generators and loads, right? For example, take the European interconnected network. The same is in the US and other parts of the world. We're talking about millions of electric loads, thousands of generators, and operating very large machines that if they go bad or if something happens, human lives are in danger. OK. At the same time, all of this is interconnected. So something happens in Portugal, and Sweden is affected. And as if this was not actually enough, electricity cannot be stored. And if we lose electricity, we are talking about millions or billions of euros or dollars or whatever you want lost per day of interruption. OK. So this is something very complex. We need real-time control. And we need to be able to capture all the possible scenarios that can go wrong, right? So what is actually the goal? The goal is to make sure that everyone always has electricity, right? So whenever and wherever you actually plug your phone in the plug, you can charge your phone. Somebody's actually taking care of that so that you can do it, right? And at the same time, you must make sure that nothing never goes wrong. So how do you actually do that? We need to run millions of scenarios to make sure that we are prepared for anything going wrong. We need to take good decisions fast, ideally real time. So if we really want to do that, then we need super fast tools, right? We need very fast computations, and we need as much as possible accurate computations. So power systems computations have always been very complex. And as a matter of fact, actually, from the time that computing started, and this is actually, if you think really about it, is when the integrated circuit came to the market, the start of the 60s, power systems were one of the first applications that this has been used on. Okay. So this is actually a picture. So Carlton showed something from Los Alamos, the supercomputer there. This is actually a picture from the DTU Power Engineering Department back in the 1960s. Okay. So this was already part of the research back then. And that's why we deal so much with numerical methods. So Newton-Raphson is nothing else than a numerical method. It's standard for power flow calculations here, right? Okay. So the complexity is big, and we need to be fast. And now, on top of that, the green transition is coming, right? So we want to move towards a system with 100% renewables. This means for a few large-scale generators, we go to too many small generators that we need to control in real time, or actually they inject in an uncontrollable way, and we need to make sure that everything remains safe and everybody has electricity. Okay. So the challenge becomes drastically larger. And at the same time, it's not only that we have more renewables, we also electrify more sectors, because that's actually leading to lower carbon emissions. So the demand is increasing, the generation is changing. We're talking about many more injection points, many and more higher risks. Okay. So if you really think about that, then this compares to how aviation was 70 years ago. If you think about planes that were flying 70 years ago in the 50s or in the 40s, you were based on the physics, and the plane was floating in the air because of the physics. Okay. If you take the most modern airplanes, if you just leave them without control, they are going actually to fall down like a brick. Okay. It's actually the control, the real-time control, the continuous control that keeps them up in the air, and they are much more agile than any airplane 70 years ago. Okay. And that's exactly what would happen, or we want to happen, with power systems. So we're talking about a much more power electronic interface generation, a lot of more power electronics also in the loads. We need to make sure that we control it in a way that keeps the lights on. Okay. The power system has become so large over all these years exactly because physically it was able to. The oscillations have, let's say, the way that this has been actually interconnecting, the physics behind it, the oscillations dump. It's a physically, let's say, damped system, right? But this, with the more and more power electronics, will no longer be the case without active control. Okay. So, and all this actually arrives at the conclusion that the current computational tools are no longer sufficient. So if you think about what you are doing, you are all trying to develop new tools that are better and faster and scalable. Okay. The thing is, we're not talking about 2 times better. If we want to really achieve the green transition by 2050, we need to be 10 times or 100 times better. Okay. So we need tools that are able to capture this much higher complexity and capture also many more scenarios, because the uncertainty is also increasing very much. Now, the question actually that we came to, or that we ask is, can AI or quantum computing help? So AI and energy are actually two of the sectors that have shown, or the largest growth potential. for the coming years, and if you actually see different studies that happen there. And AI is already creating value for power systems if you really think about it. Okay. So do you know what the first application for machine learning has been in power systems? Say that again. Of what? Forecasting of? Yes, very good. Do you remember when? In the 90s. Okay. So the first application indeed for machine learning in power systems was in the 90s. The tool was called ANN-STLF, so short-term load forecasting with artificial neural networks. This was developed by EPRI, and the tool has been used by US utilities during the 90s. I mean, from they started with 2, and then it was deployed up to 32 in 1997. Okay. So this was the first application of machine learning. Then we have also many more. So if you go into weather forecasting, wind forecasting is for us very important, right? So the Google GraphCast, at the moment, the newest version, is working with AI, and it's actually performing better than the physical models that exist for global weather forecasting. Okay. So we see that AI can already maybe surpass the performance of physical models, at least for some applications. Another actually area where AI has been creating value so far is predictive maintenance, right? So the problem there is that I want to actually predict when, for example, a component will fail, and I want to perform the maintenance not too soon, but also not too late, right? If I do that in regular intervals and too soon, then actually I spend much more money in maintaining that while this is not needed. If I do it too late, it actually it leads to a blackout. So they're already using drones and different data from sensors to be able to predict when things go bad. Okay, different utilities. And it's also used in energy trading. Do you know what this is?
Gas storage.
Storage of what?
Gas, natural gas.
It could have been, but it's not. No, it's not gas storage.
Right.
Say that again.
Grain storage. Like
Grain.
agriculture storage?
No, it's not grain storage. No. Pressure dials. It's water tanks. Okay. And they use it to predict how much water we have actually stored that's going to be used for hydros. So knowing how much we have, we can actually predict what the price of electricity, or let's say how the hydros can be used. Okay. What is the common theme along those uses so far? Forecasting, yes. Okay. So AI creates value so far in all these areas that we cannot actually use physical models, or the physical models do not cannot perform maybe so well, right? If we do image recognition that we use for the drones or for this one in order to predict, physical models not really help. Probably we need some kind of AI tool to do the image recognition or image detection, right? Same with weather forecasting. We're talking about something extremely complex. There is that's actually where AI offers value. We have seen nothing when it comes to the real-time operation or the safety critical part. Okay. Now, AI can do, however, a lot of more things, and this is actually a graph for the training costs of ChatGPT and the likes. For 2023, the Gemini Ultra from Google actually had a cost of about $200 million spent on training. Right? So if companies spend so much money on training an AI tool, it can probably do a lot of things, right? And if not in 2023, maybe 2025. Okay. We're talking about a lot of money invested in these tools, and all these capabilities are bound to increase. So right now, actually, it can be a virtual assistant. It can be a live interpreter. I mean, if you go online, actually, there are tons of videos of what these kind of tools can do, right? But would you ever trust AI to run your electricity network? Could you get one of those AI assistants and let it run the electricity network of your country? Who's that?
Not yet.
Not yet. Okay. What is missing? Reliability. Yeah. Reliability, explainability, yes. Okay. To be honest, we are not very comfortable yet to allow that to run our electricity, considering the risks that it's out there. However, AI has run a fighter jet, right? I don't know if you caught that in the news. That was just less than a month ago. The first, let's say, successfully, the first successful flight of one of the most modern fighter jets run completely by AI. So trustworthy AI has been necessary to be able to fly this. And then new questions also arose. Will I trust my AI or any AI to pull the trigger? Who decides, right? If you operate a power grid, would you trust the AI to take a decision that might lead to a blackout of one area against the other, or any kind of decision that could be critical? So similar questions that arise with this first AI powered flight, if you want. Similar questions arise also for the control of the neural network. So what we need is responsible and trustworthy AI. Okay? And that's what we're going to discuss in the rest of this lecture. Okay? Any questions or comments so far? Okay. So what are the barriers when it comes to the machine learning applications for power systems? First, and I guess you can already imagine that, why would I use a black box to decide about a safety critical application, right? Neural network performance metric, if you actually deal with machine learning, is often accuracy, or one of them is. It's a statistical metric. All of these metrics are actually based on a test set, are all statistical. Okay? Why would I trust these statistical performance metrics and that tells me nothing about previously unseen points? It just gives me an average performance. Okay? And at the same time, good AI tools need good data. Why would we depend on data-driven approaches, so this discrete and incomplete data, when we have developed these detailed physical models over the past 100 years? Okay? So that's where actually neural network verification comes in, that can deliver guarantees for the performance of neural networks. And that's where physics-informed neural networks come in as well, that might help to better inform the machine learning models we build and make them, let's say, more dependable. Okay? Okay, there's a lot of recent developments for trustworthy AI. In April 2021, the EU Commissioner for competition, Margrethe Vestager, actually happens to be Danish, put forward the vision about a Europe fit for the digital age. If you really see, actually, Europe is taking concrete measures for a robust use, as I call it, of AI. Now, if you apply for a European project or a European research project, in the evaluation, the evaluators should also say, do they use AI? Is this robust? Can we trust it? Okay. So the idea was first to actually protect the consumers, and then actually to protect all the users of AI, whatever it is, companies or other entities. Okay. Tools are getting developed to be able to verify neural networks. Okay. Gurobi, which is actually probably the world-leading piece of software for mixed integer optimization, since last year they have a module for machine learning or neural network verification. Okay. And this year actually it was also improved. So it's even better this year with the Gurobi 11. There's a competition. So if you want to participate, so Carlton's actually colleague Hassan Hijazi participated there last year. There's a competition about neural network verification. So far, the focus has been on images because that's where most of the community comes from when it comes for verification, when it comes to verification. So all the data sets so far has been mostly images. And image recognition is important because AI can be used in health, So if I do an MRI and I want to see if the person has a cancer or not, or is maybe a high probability, then I need to be somehow sure, okay? And that's where it's used also for self-driving cars. There is an effort by some people at least to also provide power system models to be verified, because that's how can also make aware that community that power system is important. We tried to do that last year. We were not actually successful to submit something. But if this is something interesting to you, you can always create a data set or use one of the data sets that you have and submit it to the competition so that actually the competing teams can verify on this, which I think is quite important. Now, a piece what I have here is actually that the winning algorithm so far has been alpha beta crown. There's a lot of development with this algorithm, and has been doing actually a very good job when it comes to verifying neural networks. And what we did actually last year, we took this alpha beta crown, that's actually the best algorithm out there for verifying neural networks, and we adapted it to be able to verify power system problems, right? What the alpha beta crown has been built for more maybe for is it safe or not, so a 0-1 decision, and we want to verify for a lot of line overloadings. So we adapted a few things, and here now is a competition. It's actually a comparison between Gurobi for verification and alpha beta crown, and you can see that this is actually 7 to 300 times faster. And when does it get? So it's very fast to tell us if something is not safe, if it violates the constraints. Why? Can somebody think why it's much faster to verify if I violate than if I comply with all specifications? Yeah.
You just need one.
Yes. Right. So the moment you violate the first constraint, you stop. To verify that you are compliant with all constraints, so all lines do not violate the line limit, then you need a lot more effort, right? So the difficult part, and that's what the computational demanding part, is to verify that the neural network is compliant with all specifications or all constraints. Yeah?
So this is really the question of how can I trust alpha beta crown model that is able to really verify the model? So this raises me the question of how can I trust alpha beta crown model to be able to really check if my model is safe or not, trustworthy or not, because if you cannot try all combinations that can happen, then there is no point in verifying. Okay, you can verify that it does not verify some constraints, but not all cases. So how can I trust the alpha beta crown? I can just say, okay, it's safe for those constraints, but not for all constraints.
So alpha beta crown does not decide which constraints you are going to verify for. You have to tell it, please verify for those constraints, and alpha beta crown checks the entire input domain of your neural network for these constraints.
So if I forget something?
If you forget something, then it's your fault, not alpha beta crown's, right? But it's a matter of, so I am the one that should certify. Alpha beta crown is the tool to certify with. If I don't enter a specification, it's my problem. Is that clear?
Yeah, it's clear,
But
okay, I understand that it checks a lot of constraints, but I'm still really doubting about those kind of methods to verify the trustworthiness of AI, because yes, for me it should be tested in a lot of cases. And so what I would like to see if AI is trustworthy or not is that I would compare a model, an AI model with another model and say, okay, this one is safer or I don't know. But it is the only thing that I can say for one given model. I cannot say much about its trustworthiness in every case and every possibilities.
Let me see if I have some chalk here. We don't have any chalk? Great. So here's what happens, right? What alpha beta crown will tell you is that if this is my input domain of the neural network, right? And then let's say that I have, I don't know how to best, okay, this is my input domain. And then I go to the output, and then these constraints, so all points should actually lie within here, right? Because these are my constraints. It takes the continuous domain here, so it verifies for this whole domain and checks if this all lands in here. The moment that there is a point landing here that's coming from inside here, then this means that the certification has failed. But you have to actually define which is this area that you want to land in, right? It's not alpha beta crown's job. That's Carlton had a question.
So I think the heart of your question is really how does alpha beta crown work, which is kind of what Spyros was getting at. But I wanted to remark that for optimization solvers, the same argument applies. When Gurobi terminates, you have no way of verifying if it actually gave you the optimal solution. You just believe it. Just the way, once you understand the math behind this method, you should also just believe it finishes and is correct at the end.
Yes, I mean, at the end of the day, you have to achieve this kind of zero milk gap, right? And that's a duality gap if you want. And that's the only thing that can tell you if you have achieved the optimum or not. And the optimum here is the verification or not. Yeah. Great. So there's not only verification, there's also different parts. I mean, we discussed, some of you also said about explainability or interpretability. In general, we should try to use this. So when we go into forecasting, maybe forecasting, verification maybe does not make sense in forecasting, but interpretability does, right? So which are these features that play a major role into the output of the neural network? So for example, here what we have is the prediction, the net production of solar photovoltaic and loads, if this will be, if the solar PV will be higher than the load or lower, right? And then through this sub toolbox that you can all use, and out there open source, you can actually understand which of the factors play the most important role in predicting if I produce more solar than my load is at the moment or not, right? And that's very important in order to understand how the neural network works in the background. Also understand which features are important, and maybe you can discard some of the features that are not so important. Great. So if I want to give you a preview of what would be the main takeaways of this talk, and or maybe, in other words, what you should remember, first of all, is that energy systems are safety-critical systems. If we want to develop neural network or machine learning applications for the power system operation, then we need to ensure that this is trustworthy in some way or another. It can be verification, can be interpretability. You decide how you want to do it. There is also ways that you actually clip the output so that it always lands in there, reducing the other performance. But you have to deliver some form of a certificate that this will not violate critical constraints. Okay. Second is, and that's what we're going to see a bit in the next coming slides, that AI needs OR. Okay. Artificial intelligence needs operations research. If you really think about it, training a neural network or many other machine learning models is an optimization procedure. What we're going to see is that verifying a neural network is also an optimization procedure. And there, actually, that's where we enter with a lot of convex relaxations. Also, Lina talked about like secondary cone and the QC relaxation that actually Carton put forward. So we need relaxations at some point to be able to solve it. Of course, then we lose the tight guarantee the moment we relax, right? Then we should actually make sure that we come back to the original optimal point. And then another piece, because we see a number of papers coming out, we do not need to reinvent the wheel, right? I mean, creating a reinforcement learning agent that tries to, let's say, optimize the voltage profile, if we're able to do that with conventional tools, why not use those? So we need to actually have a solid motivation why we use AI and what is the benefit of AI compared to anything else. Okay? And not just maybe one test set, okay, here it works better, so here it is, it will work for anything else. Okay? So let's try to be a bit more careful of how we make use of AI. Also, take advantage of all the models that we have available, if possible. OK, I'm going to skip this, but it's out there to have it. It's actually, it's nothing more than a block diagram how we think that different ideas can be organized in a trustworthy framework. The summary of that is that data is very important, and then also verification helps. But I want to focus now on verification because I guess one of the questions might be, how do we verify? Okay, and I want to give you some insights behind that that might be helpful for you. Okay, so let's start with start an application. This is just a guiding example, can be anything. I just use this slide in order for all of us to be able to envision a use case that we can then actually work with. Okay. So how would we actually do that conventionally? We have let's suppose that we want to use machine learning or a neural network to classify stable from unstable operating points. Okay. If you really think about it, checking if an operating point is safe or unsafe takes a lot of computation time. If I want to maybe certify or let's say assess 1 million points, it might take a lot of time. So what is out there in the literature is that let's maybe generate a database of 50,000 points and then train a neural network, and through that we can assess the other 1 million points. Okay. So we have a database of secure and insecure points, we train a neural network, and then we have the output, and then the usual argument is that this can be extremely fast, so 100 to 1,000 times faster than conventional methods. Okay. Good. Now, how does the neural network verification work, right? It's an exact transformation as long as we use the ReLU activation function. I'm going to explain that. So I transform all the operations that happen inside the neural network into a set of linear equations and binaries. Okay, and I'm going to explain how we do that. After that, I formulate an optimization problem, and if this is linear equations and binaries, we're talking about a MILP, okay, mixed interlinear program. And through that, this actual optimization program, I can verify or assess if the neural network output complies with the ground truth. So let's see how this works. So let's take the simplest neural network, just so that you are able to envision that. So we're talking about linear weights between the neurons, right? And then in every neuron, there's a nonlinear activation function. The most common nonlinear activation function is the ReLU, rectifier linear unit. Okay. So what is this? A piecewise linear function. The ReLU is nothing else than if the input is positive, then the output is equal to the input. If the input is negative, so here if the input is negative, then the output will be 0. Okay. That's nothing else than a max operator. I can convert that to a set of linear constraints with binaries. Okay, so what I say is that if input is less than 0, then my binary is equal to 0. If input is positive, then my binary is equal to 1, or let's say non-zero should be here. So that's, and then we have a linear functions here. Okay. So through that, one binary variable for every neuron, for every ReLU, 0 or 1, and the linear constraints. Then I can encode all operations of a neural network to a system of linear equations with binaries. Okay. So if I have this as a system of equations, then I can actually pass any kind of input and then understand what exactly the output will be. Also understand what would be the maximum output or the maximum violation of an output, if you want, for any kind of input within a domain. And that's what I'm getting at. Let's see an example. Okay. So what we did here, this is our actual data from simulations of a small system, a 9-bus system. What we see here is a 2D projection. There are two generators. So the combination of the set points for two generators, this is normalized between 0 and 100%. So this is generator 2 between 0 and 100% of its power output. This is generator 3, 0 and 100% of its power output. Okay. What we have plotted here, we have generated that ourselves just to be able to show how this works. Okay. We have generated a lot of operating points, and then we have assessed each one of them conventionally. So all the green points are the safe points, or the blue points are the unsafe points, right? And then we also assessed what a neural network does, and you can see that correctly classifies all the green points, correctly classifies all the blue points, and then the red points are misclassified. That's exactly on the boundary. Okay, is that clear so far? Okay. Now, how does the verification work? We take a random point, a reference point, and we assess the we assess if that's truly safe or unsafe. And then we solve an optimization problem. Does the classification change for any input within distance epsilon from this? If the classification does not change, then I can verify that this whole area is actually, this whole area here is classified as safe. So this is the first step, and this is actually exactly what happens in image recognition. Okay. So I verify that this whole rectangle belongs to the same class. And then I moved another reference point, and I can verify that the neural network will classify the other rectangle, again, all in the same class. Yes?
Do you choose the size? You choose the size of the square yourself?
So the question is if I choose the size of the square myself. Yes, this is part of the epsilon. You can decide that. Obviously, the larger the size, the optimization problem becomes more complicated, and you might or might not achieve that. Yes?
How does it work if we go to higher dimensional spaces? I know that normally for neural networks you could consider something like a first. How does that change when you go to higher dimensional spaces? Because obviously then it becomes, I guess, more complicated with the epsilon and the space. Do you then maybe consider something like adversarial attacks, which also are usually used to assess robustness?
Yes, I mean you can use exactly the same. You can use exactly the same setup or let's say framework to assess adversarial attacks. What you do there for adversarial attacks, and we actually the paper has that already, and also the paper we inspired from also proposes that. I just don't have it here. What you do for adversarial attacks, you say, I have this reference point here. Find me the minimum distance that the class changes. Okay, and then I can see. Okay, so here's where the class changes. Is this normal or not? And that's how I can get adversarial points. Okay. Clear so far? Okay. So this is what you can do if you have classification and also maybe difficult models to verify. I'm going a step further with provable worst-case guarantees because in power systems, we have maybe some things that we can take advantage of, and that's actually what we came up with. Okay. And the key enabler in power systems is our ability to represent the underlying ground truth. Actually, we have created the models that represent the system. And theoretically, we have created models that are pretty accurate. Okay. As long as we trust the models, then we can include them in the verification, so they can be part of the optimization problem, And then I no longer need to go and say, you know what? So this is what the neural network does. Now let me check if this is correctly classified or not. I include the constraints in there, and the optimizer tells me if I am correct that I classified that or not. Okay. So the idea is that I take the advantage of the ground truth, and I can measure now the performance. And you can think of that, the worst case performance. I had some slides, to be honest, with more the math background that I have removed because I thought it might be too much. But we can discuss, and I can actually use the board if you want about that, okay? Good. So the cool thing here is that I no longer am relying on sampling. I have my full input domain, and I can verify for the full input domain, and I can get what? The worst case violation, okay? For its input domain, now I can get what is the worst case violation of my line limit or my voltage or whatever. Okay. So let me show you some tests that we run. This is now for OPF. Okay, but maybe that's not, yeah, please.
So my question might be a little bit fundamental, but I was wondering, in many real application of the power system, for example, in forecasting, so we are training AI and algorithm or machine learning in a database that we had, and we know the labeled database, so the training and the testing sets are known. But when we want to apply to the other, like the data sets, that the real application, for example, if you're training on a data set located in somewhere of the world, and then you want to apply to the other part. So in the target data set, you don't have actually the labeled one. So there is just only unlabeled. So how you can say, let's trust about the results, and how you can validate the accuracy of the results?
For that case, or how this can be transformed to a verification case? How can we transform it, right? Yeah. So for forecasting, so let me actually explain how this will work. The idea is that what happens conventionally is I have this, as you said, the test data sets. These are discrete data points that are labeled, right? What I can do here is I'm no longer talking about discrete data points that are somewhere here. I am talking about this whole domain. So what I can verify is, so let's say, I don't know, what could be the input? Could be, let's say, temperature, and the output could be wind speed. Shall we say something like that? Okay. So instead of actually having some discrete temperatures and then how this map into the area of wind speeds. So let's say temperatures here, right? And then wind speed here. Then if I want to use this framework, I can say that for all these temperatures here in this box that can be maybe two-dimensional, so maybe two different sensors, right? All of these land inside here. And in that way, so you need actually to get a superset of your label points, right? So what you can verify is that none of the predictions will land to a wind speed that's completely off. And that's what we can verify for forecasting. But the cool thing is actually that I don't, to find this point normally, I need to run I don't know how many points here and be lucky in finding this. Right? Here with the verification, I don't need to think about points. I can just ask for this whole domain, is there anything that's completely off? And as long as you're able to solve the optimization problem, it can tell you. You don't need to rely on luck. Okay, let's try another, I don't know, make it more granular to see how this works. Performance. Clear? Okay. Great. So what we did here is we ran that for 7 different power systems. And what we compared is, again, this is an OPF. So what I'm trying to do is I am trying to estimate with a neural network the optimal set point of generators, right? That's the minimum cost. optimal set point, but at the same time, the set point should not violate any constraints. And what we're talking about here is constraints related to the power limits. So all the generators should be, the set point should be within limits, and line limits. So if I get the optimal set point, should not violate any of my line limits. Okay. So we trained the neural network, and actually we trained it with like 99 point something accuracy, right? So we did a good job in training the neural network. And then what we did is we tested the empirical bound. So we took all the test and training data that we had, and we measured what is the worst case violation. And then we also used our approach that does not need to take data anymore. You just tell it, so this is your domain, get me your worst case guarantee, your worst case performance. Okay. So I'm just going to focus on 2 points here. So from the test and data sets, test and training data, this is actually the worst case performance that we were able to find. But that was for a point that we use for training, right? Inside this domain, there were different points hidden, and these were actually 7 times worse in terms of violations. Okay. So although we get a good average performance, we can still get violations, and the true violations might be hidden somewhere inside the data points that we have not considered, because the neural network might have found a good, let's say, optimal set point in terms of, I don't know, maybe OPF, or let's say optimal point, but still it might land outside our constraints. And this can be 7 times larger. Another cool thing is for a different case that we can also get 0. What does this mean? That this neural network, as it was trained, is guaranteed to never violate the line constraints. Okay? Yes?
How are you able to guarantee that it will never violate?
So the question is, how am I able to guarantee that it will never violate? And the answer is, considering that I put the constraints here, right? And I have so I have the equations modeled inside my optimization. So I tell it, let me know what is the maximum violation of the line constraints. If this is 0 or less than 0, this means that it will never violate. So there's no point here that will result to a positive number here, so which means a violation, right? Yeah. Yes. How do I?
How do you define the boundary of the input?
Yeah, now that's a design variable, so a design decision. So what we did here is we said that the load should vary between 60 and 100% of the nominal. So for all this, so these are different. So let's say that this is load 1, if we are only if we are in 2 dimensions only, and load 2. So 60% here, and 100% here. So for all these combinations of loads, find me the optimal set points, or it's trained actually to find the optimal set points for all the combinations of loads. And now through all these combinations, what is the worst case performance? Is that clear? Yeah. It can be also 40%, or it can be whatever you want. We limit it to that point. And to be honest, if you go too large, then your optimization or verification becomes problematic, right? I mean, it's very complicated to verify. So you need to find ways to make it scalable or to split it into smaller parts. Yes?
So I might have a bit of a naive question, but since we can find areas where we have a large violation of the constraint, can't we reverse the process to find ways where we should do more samplings and then get more data and improve the...
That's the next step, right? Okay. That's very good, yes. So the next step is actually, that's exactly what this can help to. So first is actually get some kind of trustworthiness. So this is what the worst case violation, but then let me see if I can just show it here, because we have it. So you do the verification, and then you enrich the database here with the verification informed, with the verification informed sampling here, right? So that's the, yes. And that's actually one of the cool things if you do then you can improve the performance of your model. Yes. Other questions? Okay, let's move on. Great. So what is the vision, at least from our side? And so the EU is actually pushing forward for validation certification of AI models. So there was a recent call for European research projects to develop a testing and experimentation facility for AI in energy. Okay. So we were one of the winning projects. So actually this starts now in October 2024. The idea is that we work across Europe, so many different partners, to develop this kind of facility that will be both software and hardware. So we have our labs. The idea is that AI vendors can bring their tools. We have the processes to certify or verify them or validate them or however you want to call it. There are going to be different algorithmic tools based on the specifications that the users, that can be utilities or others, put forward, so that by the end, we give a stamp that, you know what, this AI tool is certified, you can actually use it in this application. Okay. That's the overall vision. I'm not sure if we're going to get there in the next 3 years, but that's the vision of where we would like to go. Okay. And related to that is also that, or that's more maybe one of my thoughts, but I think also others, that we need to create standards. So the idea is that AI tools, we want to enable AI tools in the energy sector, but let's create standards of how this, that they should comply with. Okay. Yes.
So you're going to certify that, for example, these AIs we can use for this, for example, forecasting problem. So are they going to be like used in an online manner or an offline manner?
In what sense?
Online manner or offline manner, for example, this AI is going to be like just like produce new forecasting like on daily based routine or something?
To be honest, that's part of the tool, right? That's. I guess it can be both. Why this doesn't play a role for the certification?
Yeah, so that's now there is a question raised for me here. Yeah. So how you guarantee the atmosphere of like implementing that AI? Because you know that an AI could be very trustworthy, like in certain circumstances, but it could be poisoned. You know, so you can't guarantee it because you're not going to use it. So you don't know how. You can't guarantee its integrity because you don't know the security of the circumstances they are going to use it.
Can you give a more concrete example? Because I don't think I completely.
Yeah, gotcha. So, for example, say they are going to like implement it somewhere with some like data set, like they're collecting some online data sets. So, but these data sets could be poisoned by some adversaries. So your your like label could be under question at some point because maybe, you know, under like some problematic data sets, it's not going to work well. So
okay. So in that case, what the verification will do will say that for this data, this is my answer. Now, if the data is poisoned or not, this is something I cannot certify. This is a different part, right? But for this set of data, as long as this is the data that you input to me, that's what I'm going to give as an output. And then it's a different part that we need to verify that the data is not poisoned, or let's say, right? Yeah. Yeah, very good. And then another thing that we're working on at the moment, and we have a manuscript out, but not yet published, is what we call this kind of minimizing worst-case violations of neural networks by design, in a way. So the way is that we want to develop a neural network training algorithm that at the same time minimizes the worst-case violations. And we can do that because we're actually able to represent the ground truth inside the neural network training. Okay, we have the models, and as long as we trust the models, we can include them in the neural network training. So you can think of adding a regularization factor, so an extra objective in a loss function to minimize the worst case violations of that. And ideally, I'm coming. And ideally, what we would like to see, for example, at the end, neural network training finished, accuracy is 19.2%, or the RMSE, and the worst case violation is 10%. So at the same time, I train for both average performance and worst case.
I just have a quick question about the minimizing, because I just also thought about that, including this in the loss kind of as a sort of regularizer. But how do you actually do that? I mean, I can read probably the paper, because I guess the worst case you calculate with the optimization problem, right? Which is very hard to differentiate, which is usually the necessity for your loss function. So do you some approximation or some sensitivity on the optimization problem? And also, how does that scale again? Because if the optimization problem gets very big, then the calculation takes very long, and then the differentiation also is like very computationally inefficient.
Excellent. Yes, these are excellent questions. And these are actually challenges that we faced. So what we did is, so what we're trying to verify, or let's say the correlations, is a nonlinear set of equations, right? So what we did is we linearized that, and then we used that as differentiable layer. And that exists, so I can use a linear program as a differentiable layer, so I can actually backpropagate through that during the neural network training. And that's how we actually include it in the optimization. And yes, it's difficult to scale, and yes, that's actually one of our challenges at the moment, how to scale that, because it becomes very complex. And one of the ways to scale it is, instead of including both of them in the same optimization, to do that iterative, alternate, one iteration about optimizing the neural network, one iteration about minimizing the worst case violations, and alternate between the two.
I think we all want to be able to verify like a large language model with 1 billion parameters. What are your thoughts on the future of scaling? Is there a path, or do we need just totally new methods?
That's a great question, and to be honest, I don't have a definite answer. I mean, right now, verifying like ChatGPT is impossible, right? Yes. And indeed, we're talking about relatively small-scale models. For us, it has been so far 4 layers with 100 neurons per layer, right? Which is, so what I think it will happen is that we will start at least with, let's say, control problems. It can be inside an inverter. So I can have an AI controlling an inverter that maybe I don't need to have such a complicated neural network. And then gradually we will scale up. For the larger machine learning models, then what can work well is the so-called clipping that actually Pascal Van does as well. So instead of verifying, I can just tell my neural network that any output that violates the constraints is discarded. Okay. Or I somehow push it inside. That's faster to do it. It's obviously it's not maybe the best performance because the neural network has been trained in a different way, and you might lose some of the performance. But I think that a combination verification and this kind of clipping of the constraints of the bounds, so in order to bound the output inside the feasible space, that can work for larger models. Other questions? Okay. Now, I'm going to talk a little bit about physics-informed neural networks. Are you tired? Do you want a break? Okay. I have a few slides on physics-informed neural networks, and then we have the tutorial. You are welcome to actually go through it or take a coffee and then come back and look into it. Right? Okay. Okay, so a few things about physics-informed neural networks, because this has indeed seen, let's say, a lot of interest over the past couple of years, including power systems. And the question is why? Okay. So there are 2 main reasons why. The first is that if I can train a neural network to, let's say, represent differential equations and represent them accurately, and actually a neural network has been proven to be, let's say, a global approximator. So in theory, with enough weights and neurons and layers, I can represent any set of functions, right? At the same accuracy. So if I manage to do my job well and get a neural network to represent, let's say, a set of ordinary differential or partial differential equations, it's much faster for me to evaluate the neural network than a set of ODs or PDs. And why is that? Because when I solve differential equations, I have to integrate. That's an iterative procedure. I need to go step by step. If the rate is too high, then I need to have a smaller step to be able to arrive, let's say, 1 or 2 seconds later. With a neural network, I have trained it to predict, let's say, 2 seconds later. It's a feed-forward, just matrix multiplication, and I arrive directly there. Okay. We're talking about 100 times faster or more. That's about neural networks in general. Okay. And then we come into why physics informed. And that's actually pretty cool because through the automatic differentiation that also actually Carlton talked about, we are able to include the physical equations inside the neural network training. Why is this cool? Because so far, I should have created a data set, which means I have simulated 1 million points conventionally, then trained my neural network, and then use this neural network to assess the next 10 million points, which is fine, as long as this 1 million points of training data did not take so much time. If I include the equations inside, I don't need to spend the time generating the data, so integrating for this 1 million points. What I do is I just include the equations, and I evaluate the equations to minimize the violation. I will have a slide about that during the tutorial, okay? And you will see that. But the main idea here is that I no longer need to compute. Obviously, the PIN training, so the physics from neural network training, takes longer than normal neural networks. And then it's a trade-off. How much did it take for my physics, my PIN to train, versus how much time it took to generate the data and train a neural network? And then if we go into differential equations, the benefit is clear. For algebraic equations, it is usually better, but not always, okay? Depending on how complex things are. So these are the two main reasons why pins receive interest and why they should actually receive interest, because there are also many other maybe motivations, but these are the two main ones that are worth, that make pins worth looking at. Okay, so what I'm going to show you here is actually some results from my collaboration we had with Ørsted. Ørsted is the largest offshore wind developer, I think in the world, and actually also a large company in Denmark. So what happens with them is that they get these contracts to design wind or to build wind farms, and they spend a lot of time during the design of the wind farms to tune the controllers, right? So which controller is best, or actually how to tune the controller to make sure that it's going to be safe. We're talking about maybe 14 days of simulations, electromagnetic transient simulations, which is a set of ordinary differential equations, quite complex, in order to, for example, tune different controllers. So if they are able to develop approaches to reduce this time, this can help them during the design. And you have also heard from Julia yesterday that before even we go to the landowner, there's a ton of different studies that happen. If we are able to accelerate the studies, then we can reduce the time that it takes to build a wind farm. Okay. Okay, so here's the idea. That's let's say, a simple, if you want, case. What we do here, we have a wind farm, and we want to tune the PLL controller, phase locked loop. If you don't know what this is, it's fine. It's a controller. Okay, I want to tune the parameters. So how do I do that? I want to estimate the region of attraction of the controller for different parameters for different control parameters. What if you do all know what the region of attraction is? Okay. So what the region of attraction is that I have an initial point that's not in equilibrium, right? So I am somewhere off my steady state, and I want to see if I will converge in the next second or 2 seconds in my steady state. So if I'm not that far away, somehow I get this attraction that I go back to my equilibrium, and that's because the controller is designed in such a way. You can think of that as a swing that a mass and a spring, right, from a wall. If this is equilibrium and actually pull it a bit here, then it will oscillate and will come back here, right? If I pull it too much, it will break, and actually it will go somewhere else. And that's the whole idea. So which is the region of points that I can disturb my system and still converge to the region of to the equilibrium point? Because this means that then I am safe. So the controller is tuned in a way to attract all these points that are abnormal into the equilibrium. So, and what you can see here is actually then what we do is for a lot of different initial points, we need to perform the simulations, electromagnetic transient simulations, to see will it converge or not. So what this color map shows here, does it move? No? Or did it stop? Yeah. So what the color map shows here is for different controller parameters, how the region of attraction changes. These are the initial points, right? And you can see how the region of attraction reduces with different controller parameters. So what we compare here is actually the conventional simulation and the physics-informed neural network. You can see that it's quite similar. We cannot verify that yet, but I have some thoughts about that as well. Okay. So this is now, we can only verify or validate that by inspection. So it's not a rigorous verification. We can only see that, okay, it's quite similar. That's the best we can do at the moment. For the physics informed, why? Because we have the differential equations in there, and we cannot verify yet for differential equations. So far, only for algebraic, linear or nonlinear. And now, this is the same pin for 5 million points. Okay, and we have not run with conventional simulations. It was impossible actually to run that because we needed 2 days in a high-performance computing cluster. We can do that with the pin, 90 minutes of training and 30 minutes for evaluation. 30 minutes of evaluation can also happen on a laptop. Okay, so we're talking about 25 to 100 times faster for this case. And that's actually the benefit that we see with pins. If we do a good job training neural networks, then we can see a lot of acceleration. Now, what is the vision? The vision for us, or at least that's where we are moving towards, is to create a new simulation tool based on pins. We call it PinSim. You can think of that as a Simulink, if you want. You have drag and drop. You have different models. You have a library of models that are actually all neural networks. You pick and choose whatever models you want that maybe represent a synchronous machine or a converter or a wind farm. You put it together, and you simulate. And the idea is if this can do the job well and can move faster in time step, so longer time steps than conventional simulators can move with, then we're talking about an acceleration. An acceleration that will be 10 times to 100 times faster, depending on what kind of simulation step can I take ahead, right? So this is one of our ideas, and we're now trying to, we have a proof of concept, we're now trying, and there is also a paper at PCC that will be presented. We're trying to work more, that's about general neural networks, to develop that further. The second is we want now to interface, and we also have a piece of work there, the pins with conventional simulators, okay? Because we think that this is the way to remove the barriers. So there's so many actually industry stakeholders, they use their own tools. If we are able to develop pin models that can integrate in Power Factory, in PSCAD, in whatever, right, a commercial tool, then we can start using some of these pins, and maybe people can start trusting that if it works well. At the end of the day, a pin is nothing else than another model, the same way that you trust a model as much as you can trust it. In a similar way, you can trust a pin at the end of the day. Yes?
What language is PinSim?
Python, for now. But maybe we should talk about Julia. Eh? Very good. Yeah. So, and the other thing that we're working on, and there's also some work there, is a way to verify pins, because this is what we also think is very important. There has been work by a group that was presented actually at ICML actually a month, not even a month ago, maybe 2 weeks ago. And we also have a manuscript, because we talk about verification, so thinking about our neural network of verification, so pins, but there, the ground truth is differential equations. And if the ground truth is differential equations, it becomes much more complex to run this kind of procedures. Okay, yes?
So for the idea of pins, there is, for example, a generator.
Mm-hmm.
It was trained based on one size of the generator.
So for the idea of pinsim, you're saying?
So
Simulink, for example, these blocks would be based on some differential equations that are being solved, and then I have access to some parameters. So for a generator, I can change some of the parameters, and then I run my simulation. For a bin that was trained on a specific size, specific parameters, is it able to be parameterized, these values?
Yeah, I mean, the idea is that we train that for a range of parameters, right? So then the pin will be trained for a range of parameters, and so then you pick the parameter that you would like to set and let all the other free, for example.
So that would mean that BinSim is limited to the thing that it was trained, or would it do training every time I change a parameter? Because it has automatic differentiation, for example.
This doesn't help the automatic differentiation for that. I mean, yes, you can retrain. Depends. These are actually steps that maybe are 2 or 3 steps later, or maybe even more. To be honest, I don't know what it would be. It could, if it takes a short time to train, let's say, I don't know, seconds or minute, then maybe it makes sense to retrain for a new parameter. Of course, then this is a drawback of the tool, right, if you have to wait. Or otherwise, you just train for a wide range of parameters, and you can see that also in the tutorial. And then you just let the user pick the parameter that it wants or they want for this model, right? Yeah. It's if you are interested, we can actually discuss how you can contribute. Great. So this is about the bin verification. If we manage to do that, I just want to say that because there's a lot of work with reduced order modeling, who has spent decades producing reduced order. If you see all the dynamic power system, or let's say power system dynamics literature, we have spent decades in how to produce good reduced order models. So this means that they capture the relevant dynamics, but are also simple enough for the computers of that time to simulate. The pin is something similar, but with the verification, we can also offer a worst-case guarantee. So for the first time, we can get a worst-case performance that with conventional models, we were not able to get. With what did we get with conventional models? We keep these equations, so we capture this phenomena. But we could not say how bad or what's the worst-case performance. Still more interpretable, the conventional models. And to be honest, I really like them than the pins. But with the pins, we might have an opportunity for a worst-case performance that we didn't have. OK, and I also want to, if we want to plug this or to talk a bit about that, it's a challenge that is now online. And if you are interested, you are very welcome to join and participate. It's called ML for Physics. The idea is to generate or train surrogate models based on machine learning for power systems. So power system is mostly for the steady-state operation, to be honest, steady-state security. This is organized by SystemX, RTE, NVIDIA, and NRIA. The end date has been July 15th, but as I was informed yesterday, this will actually extend until the end of August. So I think these competitions, similar to the Go competition that we have heard earlier today and the previous days, the grid optimization in the US, it has been, the grid optimization competition in the US has been a great opportunity to actually improve a lot the OPF and the OPF tools. So through competitions, you can actually find ways to improve these tools. And we are also trying to participate, or we're participating. Let's see how well this will end. Okay. But yeah. So, and since we're talking about this, because it's focusing on graph neural networks, I have just one slide to tell you why or how graph neural networks that this competition is also focusing on can help. What's the idea, also for this competition, that I use as training data my a n-0 case and n-1, so a single component outage, and then I predict if I have any line flow violations, any voltage violations for n-2 and n-3. Why is this important? For the 118 bus case, I have 186 n-1 cases, so I run power flow for 186 cases, and then I have, I can see if I violate any of the lines for voltages. If I go to n-2 scenarios, I have 1,500, more or less. If I go to n-3 scenario, this means 3 different components out with maybe within a very limited time. Then I have 34,000 scenarios. And if you check about runtime, if I do that with AC power flow, I need 2,000 seconds for n-2. I need 14,000 seconds for n-3. 14,000 seconds is like 4 hours, right? And if I use a neural network for that, I only need about 2 minutes. 4 hours, 2 minutes, okay. As long as I am accurate. So, and we also did some work there that's now finalized, just to give you an idea. On average, if you see the average performance, if I can capture the voltage, for example, well, it might not work so well. But to capture the violation, so the under voltage or the over voltage or the line flow violation, it actually can do a pretty decent job. Okay, so that's just as an, and I'm finishing, just as an inspiration. I skip this, and then I have the final thoughts. Okay, so 2 slides and we're done. If we want to accelerate processes by 10, 100, or 1,000 times, probably we need to think in a disruptive way. So if you go with the conventional way, I'm not sure how much we can improve. If we can improve 2 or 3 times, that's probably OK. But I don't know if we can improve 100 times. Okay. So in that, if we want to think differently, I don't know, maybe AI or quantum computing can help, or something else. I don't know what this is. But we need to just let our minds free, and actually that's your job, right? You come with fresh, yeah, but that's actually, I really mean that, right? You come with fresh ideas, and let's see what we can do. And then the next would be to convince other people that this is worth doing it, okay? But first, actually, to show that it works. Yes, so AI is already creating value when there's no other option, so forecasting, for example. And it could be disruptive for energy as long as we can keep it trustworthy. Okay. People will use it as long as they can trust it for these safety-critical applications. Otherwise, I don't see utility somehow get convinced, except if we, I don't know, if we wait for 40 years, maybe things will change. Okay. Yeah, physics-informed, they can also offer a significant speed up. And one of the challenges that we see, at least, is if we can also verify these kind of pin models. And then also quantum computing, I do think that there is potential there, and it's worth looking at it. Okay. Yeah. And that's now, I finish here. Are there any questions? Great. So I stop. It's already quite a bit. You have the tutorial. Many thanks to Indrajit, who is also here. Actually, he's the one that actually coded this, with the support from Rahul and Ignacy. So what you need to do is, I guess you also have the slides. You need Google credentials. Is anybody not having a Gmail account or something? OK. So you can go to that link and get the Google Colab. And then you just need to file, save a copy in Drive. So I will just let you do that. I just want to explain 2 things, and then you can play with the code, and now Jalal will start about 20 to 3, right? Or we're going to allow for a 15-minute break anyway. Yeah, 20 to 4, yeah. I just want to explain two things, and then you can do. So these are the two things I want to explain. First, how this works. This is the standard neural network training. What we have implemented here is a single machine infinite bus. This is nothing else than, again, a generator over a line to a stiff system. It's exactly like a spring mass system, nothing else than that. That's what we have implemented. That's the swing equation. So what happens with the physics-informed neural networks is that we add one more, let's say, objective in the objective function, so a regularization factor, that this is the equations. So the neural network here actually outputs the estimate of the rotor angle, and then we get the first and second order derivatives. We plug it into this equation, and we try to minimize the violation of that. And you can actually take a look at the slides. If you don't understand it, we can discuss it again. OK, but this is the main idea behind this. For random collocation points, here we have actually taken 11 random points. We plug them in here. This is the time and the power. I think the power is constant, actually, for what we have here. And we plug them here. I'll stop here, and then you can ask. One more thing that's important, because that's how we did it with Ørsted. One option is I train from now to 20 seconds, OK, for the whole system. And then if I do that, then I can estimate anything between now and 20 seconds very, very fast and relatively accurate. If you go into larger systems, 20 seconds is a very long time to be accurate for those 20 seconds. So the idea that we used here, we train for 2 seconds. And that's what we have in your code. We test for 3 seconds because we want you to see how it performs if you go outside the domain. I have only tested for 2, but now I want to test it for 3 and see how it extrapolates. And you're going to see that it might not work so well, especially if you actually go to 4 seconds. 3 is still OK. So what the idea is that I go to 2 seconds, and I get back, and I evaluate once more from 2 to 4. And I evaluate it once more for 4 to 6, because I have trained for a lot of different operating initial conditions. OK. That's maybe too fast. Maybe you have questions. Test it, and I'm here for any questions.